我们下一个讲座呢，将由我们的资深工程师 Dalvik 给我们来讲解这个 Android 里面一个非常重要的 component， 就是我们的 Dalvik VM internals， 就是它内部是什么。这个 VM 呢，我想大家都耳详能熟了。这个它呢，刚刚那个我们 Patrick 和 Jason 呢也都多次提到，它不是一个 Java 的 VM。下面呢，我们用掌声热烈的欢迎 Dalvik， 看看他给我们带来什么，然后这个 VM 里面到底有些什么东西是非常的这样值得我们这样隆重的去介绍。好。
Good afternoon. Thank you for the introduction, and thank you all for coming here today. I'm Dan Bornstein, and I'm here to tell you a little bit about the Dalvik virtual machine. And just a little bit about me. I've been working for Google for about 2.5 years, and I've been working on the Android project the entire time, and on the virtual machine in particular. And before that, I've worked on several other object-oriented runtimes throughout my career. So this is a continuation of my kind of personal work in this area, and I'm very happy to be able to do this for Google. Although I did start the project, I can't take credit for anything but just a small fraction. There's a lot of other folks at the company who's been doing a lot of work to make it as good as it is today. And so I owe them a debt of gratitude. The name is actually the name of a city in Iceland. It's at the northern portion of the country. It's if you want to go to the Arctic Circle, Dalvik is where you catch a ferry. So you've seen this picture probably 2 or 3 times already today. I'll just show it to you one more time. As you know, Android is this full platform for mobile devices, encompassing the Linux kernel at the bottom and the device drivers all the way up through some applications. And I'm just going to be talking about this one little piece of the picture. So the Dalvik virtual machine was designed around the particular constraints of running on mobile. And if you heard Jason's and Patrick's talk, you know some of these constraints. We're not expecting to run on, by desktop standards, a fast CPU or on a system with a lot of RAM. And in addition, we don't use swap space, because on a mobile device that generally doesn't make sense, because that would eat into the battery as you would swap back and forth to your hard drive or your flash memory. And in addition, of course, we're powered by a battery. And this, I know Patrick talked about this and Jason talked about this. A lot of the design decisions come back to how we can do stuff to preserve the battery life as much as possible. So now that you know a few of the constraints, I wanted to talk about 2 areas that that Dalvik is in particular designed around, or the two areas which we paid special attention to. So the first one is memory efficiency. As I said, we aren't expecting to run with a lot of memory at the low end, so say 64 megs. And as a full platform, we don't expect there to be a lot of room left over once the essential services are started. If your device is going to be a cell phone, well, it had better be able to say, answer calls. It had better be able to look up contacts. All of these things. So these are the essential services of being a phone. And we want to be able to take whatever's left over and make as much use of that as possible to have, say, as many simultaneous applications running as we can. And the one additional thing in terms of our platform is we do want to provide a fairly rich set of APIs for developers to use, and those come at a cost. So on our system, we have approximately 10 megabytes worth of system libraries. And if you add that all up, of course, without doing anything special, that doesn't leave a lot of room left for applications. So this is the problem. And this is a picture of part of the solution. So when you run an application on Android, it first gets converted at build time into this thing that we call a DEX file. And this is just a very high-level picture of what a DEX file looks like. You can see that at the top there's a header, and below that there are these 5 sections that are constant pools. Each of these pools has a particular type of data, and you can see examples of that off to the sides. And after that, there's a couple of sections. One defines all the classes in your application, and the other is the auxiliary data that's used by all the other sections. And each of these is pointing back and forth at each other. And the pointers are in the form of either an index or an offset. So an index might be for the string IDs. Each string has a number. And if you need to refer to one of them, you just refer to that number. And so it's fairly compact. And as I said, we convert the classes to DEX file at build time. The tool that we use is called DX. And you can just see here a very simplified illustration of how the different pieces of data from the .class files turn into the different sections in a DEX file. So as you can see from the previous pictures, we have this one set of constant pools for the entire application, as opposed to in .class files where each individual class has its own constant pool. So here are just a few example classes, and I'm going to dissect them for you in the next few slides. So this is how those classes look as .class files. You can see the data in each one is its own little world, and you can see that there's a lot of duplication there. So for example, you can see that these method signatures, not only is the method signature duplicated in each of the files, but within the method signature there's a lot of duplication. In addition, you can see that there are these string labels, and these are labeling different pieces inside the file. So that's what it looks like as .class files. And here's the same data as it might look in a .dex file. These pointers, as I said, the arrows really turn into these offsets or indices. But what you can see is there's a lot less duplication. So instead of having that method signature 3 times and those class names, I don't know how many times, there's just one reference for each, and they're all shared by having them pointed at from different places. So the point here is that sharing a set of separately typed constant pools among all of the classes significantly reduces the amount of data needed to represent any given class. And in addition to what we do for this sharing, we also are careful about what data we actually represent in each class. And if you have questions about that, I can answer those during Q&A. So here's some statistics. I measured these about a month ago on our system. The top numbers are for our core system libraries, our common libraries. The middle one is for the web browser, and the bottom is for just the alarm clock application, which is just it's a small application. So you can see the different sizes of things. And within each one, there are 3 numbers. The first number there is the number of bytes if you looked at the original .class files uncompressed. So that top number is something like 21 megabytes. So if you looked at our core system libraries, and you uncompressed it all as .class files, it would be about 21 megabytes. And that middle number is what that size is as a standard .jar file. And you can see that you save about half by having a .jar file, which is not bad. And the bottom number is those same classes represented as an uncompressed DEX file. So you can see that a DEX file tends to be a little bit smaller, an uncompressed DEX file tends to be a little bit smaller than a compressed jar file. And the fact that we can have reasonable savings and a reasonable representation as an uncompressed format is significant for our platform, and I'll talk about that in a few minutes. So, you can think of any system, any modern operating system, as having 4 kinds of memory. And these are really 2 kinds of memory, two sets of a pair of distinctions. The first distinction is clean memory versus dirty memory. And the difference here is that dirty memory is memory that is allocated by an application explicitly. So if you have in say Java code, if you say new and then name a class, that effectively becomes dirty memory that the operating system must keep in RAM because it doesn't know how to recreate it. On the other hand, clean memory is memory that is known to the operating system at a low level to be something that it can recreate. And the typical way it gets recreated is by reloading from stable storage, from flash memory, for example. And the other distinction is shared memory versus private memory. And this is a fairly simple distinction. Private memory is memory that's used just by one process, by one application. And shared memory is memory that is used by multiple, where the same memory is used by multiple applications. So, in general, having shared clean memory is the best. That means that multiple applications are using this clean memory. They're all sharing the cost in it. On the other hand, private dirty is the worst. That means that you have some amount of RAM that is just used by one application, and no other piece of the system can share it. And the more private dirty memory you have, the higher the pressure is on your RAM. So in Android, this is how things break down. We have, as clean memory, we have DEX files. And this is why having them uncompressed becomes important. We can map in the DEX files, memory map it, and if the kernel decides that it needs some pages, it can always drop those pages from the DEX file because it knows it can just simply load them back in from flash on an as-needed basis. So that's our clean memory. Our private dirty memory is the heap memory associated with each application. And as I said, of course, we want to minimize that. And so the question is, how do we get stuff to be instead shared dirty memory? And the answer is something that has been introduced to you in the previous 2 talks. It's this thing that we call the zygote. The zygote is this special process that starts up early in the life of the system, and it's responsible for loading up a bunch of classes, and these are the classes that seem to be used across multiple applications. The zygote process starts up, it loads these classes, and then it has a memory heap just like any other process. But what it does is it sits on a socket and it waits for commands, and when it gets a command, it forks. And as soon as that fork happens, you now have shared memory. And so it becomes shared amongst all of the applications that get spawned from the zygote. And this is just a simple illustration of what that looks like on a system. And so that answers the question of how we get shared dirty memory on our system. So instead of every application having to have an entire heap all to itself, the pieces that we can make in common, we try to do so, and that's done by using the zygote. So there's a wrinkle in this. As you probably know, the system is interpreted and it's garbage collected. And when you have garbage collection, you have to pay, there's some special attention that you have to pay. When just looking at a single process, there are a couple different ways in which you could arrange the memory that you use during garbage collection. So you often need, say, these things called mark bits, and mark bits are read and written while you're garbage collecting. And in a single process world, there are 2 common ways of doing it. One is to have the mark bits living next to the data of each object. And the other way is to have the mark bits as this sort of separate area. So you have objects in one area and associated mark bits in another area. And you can make arguments about cache locality to say that, during a garbage collection, it's good to have those mark bits near the object data that is about to be scanned. But on the other hand, if you keep the mark bits separate, then when you're not garbage collecting, you have better cache locality. However, the debate can go really either way in a single process environment, but in a multiple process environment, there are these extra constraints. So we do have separate processes, and these processes all have to live on the same device. And the garbage collection of each process has to be independent. And we had better make sure that the garbage collection isn't going to mess with our memory sharing. And as I said, when the zygote forks, it makes copy on write. And so its heap will start out being shared, but if you write anything into it, as soon as that happens, it becomes unshared. And so that meant that there's really only one answer for Android, which is that we always keep the mark bits separate. And so when you look at that zygote heap, all of that data for the zygote heap is never going to get touched by the act of garbage collecting. And that makes it much more likely for that memory to remain shared throughout the life of the system. In addition, there's just one other advantage to this arrangement, which is that most of the time, as I said, an application isn't garbage collecting. And of course, we have several processes running simultaneously on the system. And because of that fact, we don't even have to have the memory for those mark bits. We don't even have to have it allocated until the moment we do a GC. And so that means that there's that much more memory left for the system to run the applications. So that was a bit about memory, and now I'm going to tell you a couple things that we do in order to have better CPU efficiency. So the problem here is that, again, by desktop standards, we're not expecting to run on anything that's too powerful. So you can see the CPU at the low end might even be 250 megahertz. The bus speed is going to be very low, and we can't count on there being much data cache at all. Almost nothing by desktop standards. And again, very little RAM is going to be available or could be available for an application. So before I tell you what we are doing to address it, I'm going to tell you one thing that we're not doing. So we're not doing just-in-time compilation. And the rationale here is really that for many applications, in fact, for most realistic applications, we can get away without having to do anything too fancy in terms of interpreting code, in terms of running the high-level code. And that's because we've committed, well, on one hand, we've committed to providing a lot of native code support for the heavy lifting, so for things like video and audio and graphics in general and networking. All of these things we commit to providing good native support for. And so what that means is that most of the high-level logic tends to be the stuff that it's hooking things together, or it's doing it will build up stuff and then call through to the code that's fast and native. So the short version is really you can always come up with an application that could use a little more CPU, but there's so many applications for which it really doesn't matter, and so that's why we decided not to do that as part of the 1.0 version of Android. So that's what we don't do. Here's a couple things that we do. So one of the things is that we verify DEX files when they're installed. Verification consists of going through a DEX file and looking at all of those indices and all of those offsets and making sure that they all point to other places in the DEX file that are valid offsets that are that represent the data that is expected given the structure of the file. And we also walk through the code to make sure that it doesn't violate the safety constraints of the system. In addition to verification, we do some amount of optimization. And you can see a list of some of the things. And so, for example, we do static linking where we know what version of the core libraries are on a particular device. And so at install time, we can say turn symbolic method references that have a name and a prototype and a return type. We can turn that symbolic data into a simple offset, so that when it comes time to invoke that method, it's just a simple lookup in a vtable instead of a more complicated, say, binary search or hash table lookup. So one of perhaps the most radical thing that we do in the DEX format is have an entirely new bytecode. So this bytecode is register-based instead of stack-based. And what that means is that when one method calls another, there's a stack, so one method calling another. But within each method, it's all registers. There's no stack, there's no mini stack inside the call frame for one method. And we do this in order to save on, mostly to save on memory access. And we do that in two ways. One is that we can pack more meaning, more semantics into each instruction. And so that means we can dispatch fewer instructions during the processing of a particular method, and that means that we can read a lot less from the instruction stream and read a lot less from some of the internals of the interpreter. And it's also the case that with the registers, because we can point at multiple registers within each instruction, we can avoid doing a lot of extra motion between one memory location and another within that method frame. And these are just a few statistics about the savings that we get, and I'll walk through those in just a second. So again, I measured these on our system about a month ago, and it seems to be pretty stable. We have about 30% fewer instructions than the original .class files that we came from. And we have 35% fewer code units. But we do have more bytes. We have about 35% more bytes. So each method tends to get a little longer, but we still get an advantage from that, because in the original, the code unit is 8 bits, is 1 byte. So in order to read the original instructions, you're reading it, say, a byte at a time. Whereas for us, we use a 2-byte code unit, 16 bits. And so we go through the instruction stream effectively twice as fast. So in the net, that becomes a win for us. And now I'm just going to walk through a couple of examples so you can see how DEX files look at the bytecode level. So this is just a simple function that adds up the contents of an array. And I'm going to show you what it looks like as a .class file and then as a .dex file. So here's that code decompiled or disassembled as Java bytecode. The part in red, that's the inner loop. And I've shown the statistics for that loop. You can see that there's 25 bytes in it. There are 14 instruction dispatches. And if you add it up, you can see there are 45 reads and 16 writes. The annotations off to the right show you where each of those reads and writes are happening. And this is those statistics are what you would get for a simple interpreter of this bytecode. You could save a few reads and a few writes by doing something clever on the order of about 6 reads and 6 writes. So that's a .class file, and here's the same code as a .x file. So you can see there's a lot fewer instructions, as promised. And you can see here we have, in the inner loop again, about 18 bytes total, and only 6 dispatches, and many fewer reads and writes. 19 reads as compared to 45 in the .class file, and 6 writes as opposed to, what was it, like 16 or something like that. And again, the fewer dispatches are huge for an interpreter because each instruction that you have to dispatch it really eats into your performance. Because of course, when you're dispatching an instruction, you're not doing the work that the actual code wants to do. So that's overhead that we can help get rid of. And so that's it for the first example. So here's the second. So sometimes you just need to represent an array of data in your code. And so you have to do something along these lines. Unfortunately, if you look at how this looks in a .class file, it's not pretty. That 7-element array turned into 44 bytes of instructions and 35 bytes of constant pool reference, and a lot of instruction dispatches just to initialize that array. And if you have a large enough data table, this can be a real problem. So many people are aware of this, and there's a standard way to hack around the problem, and that's to represent your data in a string. And you can see here, this is the same data represented as a string with a loop at the bottom to initialize it. So this is a little bit better in terms of how much memory is used in the .class file, but it still has a couple of disadvantages. So that string, each one of those Unicode points actually turns into 3 bytes, even though it's only representing 2 bytes. So there's a little bit of bloat in terms of that, and that loop still has to run, and that loop will take time, so that slows down your initialization. So instead, this is what we do in .x files. You can see here that there's exactly one instruction that initializes the data, initializes the array. That's the third one down. So it's fill array data. And you can see the actual data being represented at the bottom in a pseudo instruction called array data. And if you add it up, you can see that the array data is an exact representation of the contents. So there's no excess bytes used to represent that array. So for example, if you wanted to add, say, 6 more elements, you really simply add 6 more elements, and it just grows by those 24 bytes. And this is really both a speed and a space win for us. In our core libraries, it saves something like 100K. Okay, and now I'm just going to quickly talk about how the interpreter works. So this is just a very simple example interpreter, just to show what the baseline is. You can see there's a loop for the main body of the function, and inside it just simply switches on, in this case, characters, but you can imagine them being opcodes that take arguments instead. This is, again, just a simple example. So if you look at what's happening in this interpreter, there's a lot of branching. So at the top of that for loop, you have to branch into, you have to perform that switch, which branches into an opcode. At the end of that opcode, you have to branch to the bottom of the loop. And at the bottom of the loop, you have to branch back up to the top. And of course, as a toy example, you could see some obvious ways to make that a little bit better. But suffice to say that in any real world example, you're going to have all of those branches happening, at least if you write it this way. But thankfully, the folks who made GCC provided a great extension, which is called computed goto. And with this, you can, instead of having a for loop and a switch statement, you can kind of build them together into this one piece where at the end of each opcode, you directly dispatch to the next one. And this saves at least one of those branches. But you can still do better. And at this point, the toy example really breaks down a bit. But again, say a human can do much better than a computer in these limited circumstances to, say, lay out registers and how memory is used in an interpreter. And so it often is a good idea to write your interpreter core in assembly. And this slide is really the same as the last one, but you can just see how it might look in assembly. So that dispatch turns into two instructions. The first one is reading an opcode from the instruction stream, and the second one is looking up in a dispatch table to find out the address of the implementation of that opcode. You can see, again, there are two reads of memory there. The first reads the instruction, the opcode itself, and the second is finding an address. So it has to read memory to read from that table. And again, because dispatch is pure overhead in terms of the actual application code, so anything that you can do to make it faster is going to really show up as a good improvement to your performance. And so we do one extra thing. And so this is actually a version of what we do in the Dalvik VM interpreter. We've reduced it to, there's still two instructions, but there's only one memory read. And the way we do this is by arranging how the opcodes themselves are represented as instructions. So instead of them being however long they happen to be in whatever memory address they happen to be, we make sure that they're all aligned so that instead of having to do a table lookup to find the address of each instruction, we keep the base address in a register, and then we do a simple add and multiply to get the address of a particular opcode. Okay. So now that you know a little bit more about how the virtual machine is implemented, I just wanted to give you a couple of words of advice for how to write code for Dalvik, but really this also applies to mobile devices in general. So as I said before, the really big difference is the battery. If your code is doing anything, that means that it is draining the battery. So battery technology is getting better over time, but it still doesn't compare to being able to plug into an outlet. So I think about the optimization problem in terms of time scale. So at the relatively slow end are the human time scales. The human interaction scale is the rate at which someone can say type or gesture, use a mouse. So that's, say, 10 characters per second. In English is very fast. Say 30 points per second if you're doing a gesture is about all you need. Moving up from that, there's the human perception scale. And for that, you need to worry, say, about having a good frame rate for video or having good synchronization for audio. And then beyond that, there's the computer scale. And the computer scale is simply when the computer is running all out, doing whatever it can as fast as possible, just until it completes whatever task it's been asked to do. And I see the optimization problem really as attempting to push code from having to operate at computer scale up to one of the human scales. So with that, my first piece of advice is simply that an app rest as much as possible. That means that if at all possible, your app should do nothing. And of course, you really want it to do something, but the idea is that the some things that you do, that whatever that you're doing, should be in reaction to something that the user has explicitly requested, either say like reacting to keyboard input or a gestural input, or if you're say doing video, to display that frame of video and then go back to sleep rather than keep on running. Because the more you sleep, the longer the battery life, and the longer the battery life, the more, the happier the end user is going to be. So sometimes, though, of course, you do have to run at computer scale, at least for a brief amount of time. And in those cases, then you just have to be careful about how you arrange your loops. So I've shown here just 7 examples of common for loop headers. They're arranged from top to bottom and approximately most efficient to least efficient. Of these, the first 3 are about the same in terms of performance. And the first one is a little unusual. Most people don't think to count down instead of count up. It's just slightly unnatural for many tasks. So what I would just simply recommend is that if you can manage to make your loop look like one of these 2, then you're doing pretty good. On the other hand, if you find yourself having to make a heavyweight iterator multiple times at computer scale, then I would highly recommend rethinking how you're solving the problem that you're trying to solve. If you find yourself doing this, then take a step back and see if you can maybe rearrange your code some way to avoid doing that, especially if you have to do multiple loops at computer scale in reaction to, say, just a simple key press or a simple user gesture. And I just wanted to reemphasize that each time you make a heavyweight iterator, that's doing an object allocation. And you allocate enough, that means that's going to invoke garbage collection, and again, it will just eat through the battery. And that gets to my last piece of advice, is to simply avoid allocation. And you can see that if you have objects that don't live very long, that you allocate them and then they become garbage pretty quickly, well, those still have to be garbage collected, and that garbage collection, again, it takes energy, it takes time. On the other hand, if you have a long-lived object, an object you allocate and it just stays around, well, that gets back to being dirty memory, and it will probably be private dirty memory, and that increases the memory pressure on your device. So it's a bit of a bind, right? I'm saying, well, don't allocate short-lived, don't allocate long-lived. Really, what it boils down to is the allocations that you do should be in service of making your program operate more at a human scale than at a computer scale. So that's my quick advice, and that's pretty much what I had to tell you today. Again, the design of Dalvik was really in reaction to these constraints of operating on a mobile device operated by battery. We've done a lot. We've done a lot in our work to try to make it operate as well as possible in those circumstances. And simply, my advice to you is to hopefully help you make the most out of what we've done. So with that, I thank you, and I look forward to seeing what all of you developers make out of the stuff that we've worked on. So thank you very much. So if you have any questions, well, first of all, you can always go to the Google Code site, and this is the version that's in your language. And I think we still have a few minutes to take questions. Do we have the microphones? And I hope, oh yeah, okay. So if you want to ask in Mandarin, we have Bob here who can help translate.
Several questions. The first one is about the memory management. You talk about separate and share and private and clean.
Yes.
So all the things are on the RAM, IAM, but how about the non-volatile memory?
So the virtual machine doesn't have a lot to say about how we manage non-volatile memory.
I think such as like object in the object-oriented language, they have some variable or member variables and such as methods stored on the non-volatile memory.
Yeah, so we do have so this is at the library layer.
Yeah.
In the library layer, we have a few different facilities for storing stuff non-volatilely. We have the SQLite database. That's so your application can have an associated database. It can also have a general file area that it can write to.
So you see the runtime object and variable are all loaded to the RAM.
Yeah. So the operating system doesn't do swap, and that's really what it amounts to. So the RAM. So when you do something in RAM, it really is going to just stay in RAM.
Okay. The second about is the instruction set. Totally, there are how many instructions in the Dalvik virtual memory machine?
I think there are about 220. Around 220, and some of those there are a few different variants of, like, there's the same instruction represented in 2 or 3 ways for some of them.
So I think the PPT you see that is about 35% lesser than the standard Java virtual machine.
I'm sorry, the what?
35%.
The number of code, the number of code units gets reduced by about 35%. Yes.
You see that no stack code, such as in core method. So you invoke special or invoke static method. So
those are Java bytecode. So we don't actually have invoke special. We have a different thing.
You see that the register machine.
It's
But no stack code stack. Core method we should make a method frame to call the invoke special or invoke static Java virtual instructions.
Right. So the way that works in Java, as I'm sure you know, you push on the arguments, and then you call invoke, which pops those arguments effectively to make a new frame. For Dalvik, the way it works is there are actually 2 variants of the invoke instructions. One of them can just simply take 5 register references, or up to 5 register references. So you can say, I want to invoke this method with register 5, register 7, register 20, or something
just like a table. You just go to the address and invoke the method there.
I'm not sure what you mean.
Forget about it.
Okay, I'm sorry.
So another question is about OTA over the air. You know the J2ME, we can download some Java and a JAD file from the air and down to the mobile device. So the Dalvik virtual machine also support the OTA application downloading.
So again, that's actually it's not the virtual machine that supports it, but it is the Android platform that certainly supports the ability to load new applications from the network. And the network can be a cell phone network, or if you have Wi-Fi, it could be over Wi-Fi.
It's already supported.
I don't honestly know how finished it is, but that's certainly our intention is to be able to support stuff like that.
Okay. Another question is about how does the Dalvik virtual machine compare to the other standard Java virtual machine? Can you cite some advantage features compared to them?
Yeah. So in fact, I tried to get to that in the talk, which is that if you look at what we're doing on the holistic system basis, our virtual machine is set up to work better with the other virtual machines that are going to coexist on the same device. And that was really the core driver for what we were doing, at least in terms of the memory stuff. And in terms of doing the register machine, the way you can think about it is that bytecode is, so let's say, for example, compared to having a JIT. When you have a JIT, the memory, the bytecode will have to get translated into machine code. That takes memory. And it also takes time to do that translation. And so anytime you do JIT, that's increasing, that's not only eating your battery for that work, it's also increasing memory pressure because you have to have that cache of machine code. So instead, what we did was say, okay, we're not going to do a JIT, but we want to make an interpreter as fast and efficient as possible. And so we tried to work within that to make it so that the interpreter could work well. And the result was, again, the system where we can end up interpreting fewer instructions, which makes it more efficient, and where we can read the instruction stream more efficiently. Okay. So maybe if there's someone else who wants to ask a question?
Last question.
Oh, okay. You promise?
About the hardware acceleration.
Okay.
Do the Dalvik virtual machine have some plan to do some hardware accelerator on the hardware device to accelerate the virtual machine speed?
Well, that's certainly possible. I'm not aware of any direct plans to do that. Okay. But you have to keep in mind that the Google involvement with Android is really on the software side, not on the hardware side. So if there were a hardware manufacturer who said, "Oh, we're interested in doing this thing to help," I'm sure we would be very eager to see it happen. But as far as I know, there's nothing like that in the works at this point.
Okay.
Okay. Thank you. Anyone else? Oh, yes, please.
I actually have two questions. So the first question is probably the quick one. Since you just said the VM doesn't do any swap, so it's running on a Linux system. So does that mean that it's not getting used on the visual memory system provided by the Linux underneath?
I'm sorry?
Because it's not doing the swap, right?
Yeah, we're not swapping. So if you have a device that has 64 megs, then your space is the amount of allocations you can do is limited to
64.
Yeah, and that's not a limitation of the Dalvik virtual machine so much as a limitation of the Android platform itself.
Okay.
So, for example, you could compile the VM for a target that had swap space, in which case the VM would take advantage of it just automatically. It's because it's simply it's a normal binary like any other binary.
Okay, I see. Yeah. So the second question is, so I didn't see any talk about the class loader stuff. So does that mean that it just put all the image together and load it once into the memory and access all the memory through the runtime or what?
So.
Because
I'm not quite sure what you're getting at.
Dynamic loaded stuff.
So we do have a class loader.
Okay.
So and the semantics are pretty standard. So the DEX file will get mapped into memory, but of course it only has to get paged in on demand. And when an application first starts out, it's whatever class needs to be instantiated. So there, again, if you saw the earlier talk, there's the whole activity life cycle. So there's a class associated with the activity, and that will get loaded first. And the act of constructing it would then say might pull in other classes, and then the act of calling its on start method it would just sort of things would get loaded kind of organically.
Okay, so the dev class is actually acting as the same rule as the jar file, right? Since you still have the concept of the class file, right?
Yeah. Well, it's not really of the class file, but certainly of the class.
Okay. So maybe we can talk like offline.
Okay.
Thanks.
Anyone else? Okay, well, thank you again. It's really been a pleasure to be here, and I hope you've had a good day, and I hope you have a good rest of the day. Take care.
好，让我们再次用热烈的掌声感谢Dan给我们精彩的讲座。